So this is the first lecture out of chapter 8. So this chapter starts by looking at this fourth quantum number. It's what's called the spin quantum number. So given the symbol m sub s, so it accounts for the magnetic property of electrons. So electrons have what are known as two spin states. One is called spin up, one is called spin down. And the possible values of m sub s are plus 1/2 and minus 1/2. So let's try to explain this in a little bit more detail. So if this is an electron, so if it's spinning, so all moving charges have electric fields, and so most of you will probably take physics 2 at some point, and you'll study electricity and magnetism. So any electric field also has a magnetic field associated with it. So this electron has its own magnetic field, so it's like a tiny magnet. So if this is spinning, and so electrons have spin, so it's either spinning like that, or it's spinning like this. And so if it's spinning like this, so that would be clockwise from my perspective. So if you take your right hand and wrap it in the direction of the spin of the electron, then your thumb will point in the direction of the magnetic field. So if it's spinning like this clockwise from my perspective, then its magnetic field is in that direction. Or if it's spinning counterclockwise from my perspective, and if I wrap my fingers in the direction of the spin, then my thumb points in the direction of the magnetic field. So now its magnetic field is in that direction. So of course the electron doesn't know which way it's spinning, but as an external reference point, if I could see the electron, then I could see it spin, either spinning clockwise or counterclockwise. And so then it can have two different magnetic spin states. So if we try to represent that on this piece of paper, so if it's spinning like that, that would be clockwise from my perspective. So if I wrap the direction in my fingers in the direction of the spin, then this magnetic field would be, so I'll use a different color for the magnetic field, then its magnetic field would be in that direction. So we would call that spin up. Or if it was spinning the opposite direction, so if it was spinning like that, so clockwise from my perspective, if I wrap my fingers in the direction of the spin, then its magnetic field would be in the opposite direction. Okay, so that would be two spin states for the electron. So now if we have an electron beam and we push that electron beam through a magnet, then this electron beam, some of the electrons would be diverted towards the north pole of the magnet, and some of the electrons would be diverted towards the south pole of the magnet. Because you've all probably played with magnets before. What happens if you put two magnets together? They'll either attract each other or they'll repel each other, right? So one of these electrons, depending on its magnetic field, its spin would be attracted towards the north pole and would be repelled by the south pole, and the electron with the opposite spin would be attracted to the south pole and repelled by the north pole. So one of the electrons would be deflected towards the north pole, one deflected towards the south pole. Because they have opposite spins and magnetic fields in the opposite direction. Right, so sometimes an arrow is simply used to represent the spin of the electron, so an arrow up or an arrow down, so that would be spin up or spin down. So spin up is positive 1/2, and spin down has a fourth quantum number, spin quantum number of m sub s equals negative 1/2. So all electrons have spin, either m sub s plus 1/2 or m sub s minus 1/2. Okay, so hopefully that made sense. So for hydrogen, so where is its one electron at? So we've looked at in chapter 7 the different orbitals, s orbitals, p orbitals, d orbitals, the different shells, the first shell, second shell, third shell, and so forth. So where's hydrogen's one electron at? Well, it's going to be closest to the nucleus, which is the 1s orbital, right? So it's going to be in the 1s orbital. So this pink circle is representing the electron, and of course in the nucleus you have one proton. So this one electron then can have spin of plus 1/2 or negative 1/2. So it can be spinning like that, or it could be spinning like this. So some of the hydrogens would have its electrons with spin plus 1/2, and some of hydrogens would have its electron with spin negative 1/2. Okay, so sometimes this is, and they're both equal in energy. So you'd have a 50-50 mixture of both. Okay, so sometimes this is represented on a block diagram. So a square is used to represent the orbital. So in this case, representing a 1s orbital. And if we wanted to represent the electron, then it could either be spin up or it could be spin down. Okay, so let's see if you can put everything together, put your chapter 7 knowledge together with what we've covered so far in chapter 8. So what are the 4 quantum numbers for these electrons? So for this electron, will spin up or spin down. So what are the 4 quantum numbers? Basically what that means is I am asking you, what is n? What is n equal to? What is L equal to? What is m sub L equal to? And what is m sub S equal to? And so we'll do the same thing for this one. So what is n? What is L? What is m sub L? What is m sub S? Gosh. Okay, so how do you know what n is? That number right there in front of the letter is n. So n is equal to 1. How do you know what L is equal to? Because you have this memorized. If you remember from the chapter 7 lectures, if S is 0, what is the value of L? It is 0, right? And if L is 0, m sub L can only be 0. That's the only possible value. And then what is m sub S? Well, that arrow is pointing up, so it's plus 1/2, right? Or it could be 1, 0, 0, negative 1/2. So hydrogen's 1 electron either has one of those 4 quantum numbers. So we can also represent this using what's known as electron configuration. So we would represent this like so, 1s superscript 1. So the 1, that is n, the s is L, and this just means there's 1 electron in the 1s orbital. So if you're asked to write electron configuration, that's what it's referring to. If you're asked to draw an orbital block diagram, then this would be what it's referring to. Okay, so what about helium? So helium has 2 electrons, right? It's atomic number 2. So 2 protons, 2 electrons if it's neutral charged. So where is helium's 2 electrons at? Well, any one orbital can hold 2 electrons. So the 1s orbital can hold 2 electrons. So both of them are in the 1s orbital. So if we had 2 electrons in the 1s orbital, so here they're both spin is, that would be, from my perspective, counterclockwise. So if they're spinning like that, then their magnetic fields would both be down. Or if they're both spinning clockwise, then their magnetic fields would both be up. Or the other possible scenario would be one to be spinning clockwise and one counterclockwise, right? So you would have spins that are opposite of each other. Or if we represented this on a block diagram, it would look, the first one would look like that, the second one would look like this, and the third one would look like that. So which is it? All possible, or is only one of these correct, or 2 of these correct, or is all 3 of these okay? Well, the answer is if you use the Pauli exclusion principle, so from an Austrian physicist, so no 2 electrons in an atom can have the same 4 quantum numbers. What that means is that this cannot be correct because those 2 electrons would have the same 4 quantum numbers, right? What would those quantum numbers be? N is 1, L is 0, m sub L is 0, and m sub S equals negative 1/2 for both. So that violates quantum mechanics. You can't do that. Can't do this because those 2 would have the same 4 quantum numbers, but you can do this, the last one. Well, this electrons would be N is 1, L is 0, m sub L is 0, m sub s is plus 1/2. And this electron, n is 1, L is 0, m sub L is 0, and m sub s is negative 1/2, right? So they have different quantum numbers. It doesn't matter that 3 of them are the same. What matters is that all 4 of them are not the same. So long as all 4 quantum numbers are not the same, that's perfectly fine. So that's the reason why any one orbital can only have 2 electrons, because if you put 3 electrons in one orbital, then 2 of them must have the same 4 quantum numbers, right? Which violates the rules of quantum mechanics. Okay, so in terms of a block diagram, then you would represent helium like this. So 1s, or in electron configuration, it would be 1s2, right? The 2 electrons in the 1s orbital. Okay, how about lithium? If we go to the third element in the periodic table, so where is lithium's 3 electrons at? Well, they both can't be in 1s because 1s can only have 2 electrons. So 2 can be in 1s, but then where's the third one at? So in order to know that, you have to know the relative order of stability of the different orbitals. So for hydrogen, it looks like this. So the 1s is lowest in energy, and then you have the 2s and 2p, which are equal in energy, and then the 3s, 3p, 3d, which are all equal in energy, and the 4s, 4p, 4d, and 4f, right? So if you remember, every time you go up a shell, you add a whole new kind of orbital. So the first shell only has the 1s, the second shell has the 2s and the 3 2p's, third shell 3s, 3p's, and 5d's, and so forth. So if it's hydrogen, that's what it looks like. So its 1 electron would be in the 1s. But once you get to other elements that have more electrons, and then you start running into electron-electron repulsions, then the relative stability of orbitals is no longer the same as it is from hydrogen. So it looks like this, what's on the screen now. So the 1s is lowest in energy, and then the 2s you can see is slightly lower in energy than the 2p's. And then the 3s is next highest in energy, and then the 3p's is next lowest in energy, and then the 4s is lower in energy than the 3d. So this tells you the relative order that you would fill up orbitals. You would fill up the 1s first. Once it's full, then you would move to the 2s. Once the 2s is full, so the 2s could hold 2 electrons. So if you have 5 electrons, then the 5th electron would have to go to one of the 2p orbitals, right? So you could put 2 electrons here, you could put 2 electrons here, that would be 4. Then if you went to 5 electrons, one of those 2p's would have 1 electron. And then how many electrons can the p's hold? Well, each one could hold 2. So you could put a 6 total. So that's 2, 4, 6, 8, 10 electrons. So if you had 11 electrons, the 11th electron would go to the 3s orbital, and so forth. So over here on the right, then, this shows you the relative order of stabilities of the orbitals. That's the order that you would fill them in. So fill the 1s. Once it's full, fill the 2s. Once it's full, fill the 2p. Once it's full, fill the 3s. Once it's full, fill the 3p. Then the 4s, then the 3d, then the 4p, then the 5s, then the 4d, and so forth. So there's an easy way to remember this, and that's not the easy way. The easy way to remember this is to use what's called the Aufbau principle, or the building up principle, or this diagram that we're fixing to go through. So this diagram shows you the order to fill electrons in when populating orbitals. So we start with the 1s, so we're going to fill it up. And then, so we're going to go up these diagonals. So once the 1s is full, then we're going to fill the 2s. Once the 2s is full, then we drop back down and we go up the next diagonal. Then we fill the 2p, and after the 2p is full, then you fill the 3s. All right, so we go up a diagonal, and then we drop back down and go up the next diagonal. And then we drop back down and go up the next diagonal. And then we're going to drop back down and go up the next diagonal. So after the 3s, we're going to fill the 3p, and then we're going to fill the 4s before we fill the 3d. Right, and then drop back down, go up the next diagonal, fill the 3d, and then fill the 4p, and then fill the 5s, and so forth. So after 5s, drop back down to the next diagonal, then go to the 4d, 5p, and 6s, and so forth. Right, so hopefully that makes sense. So again, how many electrons can go in each shell and in each orbital. Well, the 1s, there's only one line for those, right? So there's only one of each one of those in each shell, so each s orbital can only have 2 electrons. The p orbitals, if you notice, they always come in sets of 3. There's always 3 lines or 3 blocks for them, so they can all have 6 electrons total, 2 in each, right? Or the D's, there's 5 of them, right? So you could put 2 in each, so they could hold 10 electrons. Or the F orbitals, there's 7 of them. So we covered this back in chapter 7. So they could have 14 electrons, right? So the maximum number of electrons in s orbitals is 2 and p orbitals is 6, because there's 3 of the p orbitals, always sets of 3, 2 electrons each. D orbitals always come in sets of 5, so you can put 10 electrons in any of the D subshells. F orbitals always come in sets of 7, so you could put 14 electrons in any of the F orbitals. And how many would the G's hold? Well, if you see, there's a pattern that goes up by 4 each time, right? So you could put 18 there, you could put 22 in H orbitals, and so forth. And how about in terms of the shell? The first shell can only have 2 electrons. The second shell can have 8 electrons, right? Because you can put 2 in the S and you can put 6 in the P. If you went to the third shell, now D orbitals exist, so 2 plus 6 plus 10 would be 18 electrons, right? If you went to the fourth shell, 2 plus 6 plus 10 plus 14, you could put, what's that going to be, 32 electrons, right? And so forth. Of course, if you remember from the Bohr model, 2n squared lets you know that as well, right? So then you could put 50 here and so forth. Okay, so let's write some electron configurations for elements that have more than 1 and 2 electrons. So if we did this for lithium with 3 electrons, where are those 3 electrons at? Well, you can put 2 in the 1s orbital, and then you would have to move to the 2s orbital, and you can put 1 electron there, so that's 3 electrons, right? So the superscripts is the total number of electrons. And then this at the bottom tells you what shell and what kind of orbital those electrons are in. Or if we were doing a block diagram, 1s, 2s, then you can put 2 in the 1s and you can put 1 in the 2s. So the ones in the 2 electrons in the 1s have to be opposite spin, so they don't have the same 4 quantum numbers. Then the 2s could either be spin up or spin down, doesn't matter. They're both equal in energy. Okay, so if you want to boron with 5 electrons, then where are boron's 5 electrons? So 2 are in the 1s, 2 are in the 2s, and then if we're using this diagram, so we fill the 1s, we fill the 2s, and then we drop down to the 2p, and you only have 1 more electron to go, so that even though the p's can hold 6, there's only 1 in them, because you only need 5 electrons. And if we were drawing a block diagram instead, so 1s can have 2 electrons, opposite spin, 2s has 2 electrons, opposite spin, and then if we drew blocks for the p orbitals, where there's 3 of them, right? Because there's 2px, 2py, and 2pz, and that 5th electron could be in any of them, it doesn't matter which one, and it could be spin up or spin down, doesn't matter, right? You could put it in any of those 3 blocks. Okay, so nitrogen with 7 electrons, so it'd be 1s2, 2s2, that's 4 electrons, 3 more to go, so put 3 in the p orbitals, and that would be 7 electrons total. Right, so you fill a shell before you move to the next shell. Okay, so if we drew a block diagram, so what does it look like? So I drew 5 possibilities here for you so that we could cover another concept. So 1s2, 2s2, 2p3. So of these, any of them that you could eliminate real easily? Hopefully you could eliminate some very easily. Hopefully you can eliminate this easily. Why can that not be possible? Because 2 electrons in 1 orbital have to be opposite spin, so you cannot have 2 of the same spin, so that is definitely not right. How about B? Can that easily be eliminated? yes, because you did not fill the 2s before you move to the 2p. So you got to fill the 1s, and then you can move to the 2s, and then you can move to the 2p. Okay, the C is 1s2, 2s2, 2p3, so that conceivably could be correct, right? D is 1s2, 2s2, and they have opposite spins, and then 2p3 because 3 electrons in the p. E can be illuminated, right? You can't put 3 electrons in one orbital because 2 of them have the same 4 quantum numbers, and you can't fill the p before you move to the s, or before you fill the s. So that leaves us with 2 possibilities. Both C and D are 1s2, 2s2, 2p3, and they both have opposite spins in the same orbital, so which one is correct? Well, in order to know that, you need to know Hund's rule. So the most stable arrangement of electrons in a subshell is the one with the max number of parallel spins. So it's more stable to have unpaired the maximum number of unpaired electrons of the same spin. So if we look at C, basically this subshell only has 2 electrons. Let's use a different color. So this has 2 electrons of the same spin in the P shell, but this has 3 of the same spin. So D is the answer. It has more. It has more parallel spin, so that is a more stable electron configuration. So basically what this means is in a subshell, by subshell I mean like in the second shell in this 2, there are 2 subshells. There's S and there's P, right? So L is basically the subshells. So subshell, so that would be like if N is equal to 2, L can be 0 or L can be 1. So in SP, these will be the subshells. So in the P subshell, there's 3 parallel spins, and that is lower in energy than only having 2 parallel spins. So in C, one of the 2 P's has electrons paired, and that is less stable. Okay, so nitrogen is an example of what's known as a diamagnetic element. So you can have atoms or elements that are diamagnetic. So diamagnetic elements have unpaired electrons. So anything that has unpaired electrons is said to be diamagnetic, and diamagnetic compounds or elements have magnetic properties. Right? Okay, so if we did this for neon with 10 electrons, so neon would be 1s2, 2s2, 2p6. So fill the 1s, fill the 2s. That gives you 4 electrons. You need 10, so 6 to go, and the 2p can hold 6. So that would be, if you drew the block diagram, so 6 electrons in the p subshell, so they each need to be paired. So neon would be an example of a no, this is backwards. So nitrogen is a paramagnetic. A paramagnetic compound. So anything with unpaired electrons is paramagnetic, has magnetic properties. Neon is an example of a diamagnetic compound. So diamagnetic compounds, all of their electrons are paired, and they will not have magnetic properties. Okay, how about silicon? So how many unpaired electrons does silicon have? So silicon is element number 14, so 14 electrons, so 1s2, 2s2, and then 2p6. So that's 10 electrons. So where do you go after 2p? After the 2p is full, then you go to the 3s, and then after the 3s is full, then you go to the 3p. So the 3s can only have 2 electrons, so we go 3s2, that's 12 electrons, still have 2 to go, so now we need to go to the p, so 3p2, right? So how many unpaired electrons does silicon have? Is it paramagnetic or diamagnetic? Well, so all of these are full. So all of those are paired electrons. This is not full because the p can have 6, right? And if you remember, there's always 3 blocks for the p's because there's px, py, and pz. And if there's only 2 electrons, so if this is 3p, 3px, 3py, 3pz, only 2 electrons, how would you fill them in? Well, you would not pair them unless you have to, right? So you don't have to pair them. So 2 of the p orbitals have 1 electron each, so it would have 2 unpaired electrons. So it would be paramagnetic. Right? Okay, so hopefully that makes sense. Okay, so let's go back quickly to quantum numbers to make sure that you're understanding chapter 7 in the context of chapter 8. So for this electron that I have circled, what is its 4 quantum numbers? So what is N? What is L? And what are the possible values of M sub L? And what is M sub S? So what is N? N is 2. How do you know that? Because of that number there. The number in front of the letter is the shell. What is L? L is equal to 1. How do you know that? Because it's a p orbital. So if you remember S, P, D, F, L is equal to 0, 1, 2, 3. If it's a p orbital, L is equal to 1. So the possible values of M sub L is -1, 0, or 1. So one of these is -1, one of these is 0, one of these is 1, right? So it's one of those 3 numbers. And then M sub S is equal to plus 1/2, right? Okay, so that would be the 4 quantum numbers. Okay, so let's practice writing electron configurations. So let's write the electron configurations for chlorine and for barium using this diagram. So 17 electrons for chlorine. So 1s can hold 2, then move to the 2s, it can hold 2, then move to the 2p, it can hold 6, and then move to the 3s, it can hold 2, and then from the 3s you drop back down and then go to the 3p. So we got 2, 4 plus 6, that's 10, plus 2 more is 12, and we need 5 more. So 3p, 5, and you're done, right? 3p can hold 6, but you only have 5 more electrons to reach 17, so you stop at 5. And if we were doing this for barium, so barium has more electrons than chlorine, so let's just take this, save ourselves some work, and paste that here. And then let's take this and make that 3p6, and then continue on. So after 3p, we go to 4s, right, 2. And then after 4s, we go to 3d, and it can hold 10. So how many electrons we have now? 10, 18, 20, that would be 30. We've got a long ways to go. So after 3d, we go to 4p. It can hold 6, and after 4p, we go to 5s. It can hold 2. And then after 5s, we go to 4d. It can hold 10. After 4d, we go to 5p. It can hold 6, and then after 5p, we go to 6s, and it can hold 2. And hopefully that's 56 electrons. So 2, 4, 10, 18, 20, 36, 48. That's 56 electrons, right? So all I did is I just followed this diagram, going up and down the diagonals until I got to 56 electrons, keeping in mind S's can only have 2, P's can only have 6, D's can only have 10, and we didn't run into F orbitals. Okay, so hopefully that made sense. So that's difficult to write electron configuration if you have a lot of electrons, right? There's a simpler way to do this using a shorthand notation using what's known as a noble gas core. So hydrogen's 1s1, lithium's 1s2, 2s1, sodium's 11 electrons. Right, so there's an easier way to do this using a noble gas core. So if you notice, so helium's here with 2 electrons, neon's 10 electrons, argon's 18 electrons. So there is no way to simplify hydrogen, but there is for helium. So helium, so this, for lithium I mean, so that would be helium, 2 electrons. So you could write this as helium and then 2s1. So the helium would be the core, the noble gas core. Doesn't really help you any for lithium because you still had to write two things. Instead of 1s, 2s, you had to write helium and 2s. But it can simplify for sodium, for example. So this would be the noble gas core in sodium, 10 electrons. That would be neon. So you could write this as neon. And then whatever is left, 3s1. So this would be 10 electrons plus the 1 electron. So that simplifies sodium a little bit. So let's do a few more. So let's see. Well, so one thing. So if we go back to hydrogen, lithium, sodium, what do these elements have in common? So if you notice, one thing they have in common is they're all group 1 metals, all right? So another thing that they have in common is they all end in S1. And so this will be one feature of the periodic table, is that elements in the same group, in the same column, end in the same outer shell electron configuration, with some exceptions, as we'll see. So if we did the same, so keeping that in mind, if we look at bromine, so where's bromine at, and chlorine and fluorine, what do they all have in common? Well, they're all group 7 halogens. So they're all in the same group. So if bromine ends in 4p5, then what should chlorine end? It should end in a p5 as well, and fluorine should end in a p5. So we're going to just take this to simplify things a little bit. Let's copy that, and let's paste this. So if we go, and if you, let's, so we're going to cover this more in the next lecture, but this is the first shell, basically. This n equals 2, n equals 3. So here, fluorine's in the second shell, so that's going to end in 2p. Chlorine's in the second shell, that's going to end in 3p. Bromine's in the fourth shell, it's going to end in 4p. So if we just take the electron configuration for bromine and we'll back out this, back out to the 3p, right, it's going to end in the 3p, but this is going to be 3p5 instead. So add that up, that's 17 electrons. And then if we take this and copy this, and then we back this out to the 2p, right, add that up, that's 9 electrons. But we're trying to write the shorthand notation here, so using a noble gas core. So if we're at fluorine and we go backwards on the periodic table, we would run into helium. That would be the first noble gas that you run into if you go backwards. So that's going to be its noble gas core. So we could write this as helium, and then 2s2, 2p5 would be the shorthand notation. For fluorine, didn't really help you any. You still had to write 3 things, but it'll help you for chlorine. So if we're here at chlorine, atomic number 17, and then we go backwards to the first noble gas, that would be neon with 10 electrons. So if we find 10 electrons, right, that would be neon. So we could write this as neon, 3s2, 3p5 instead. And if we did the same thing for bromine, so bromine's atomic number 35. If we start going backwards, the first noble gas we would run into is argon at 18. So these 18 electrons would be argon. So we could write this as argon, 4s2, 3d10, 4p5 would be a shorthand notation for writing bromine. Okay, this is longer than I thought it would be. So if we did the same thing for boron, 1s2, 2s2, 2p1. So shorthand notation, this would, no, that is not right. Right, this would be helium, so you could write helium, 2s1, 2p, 2s2, 2p1 would be the shorthand notation. Aluminum, so it has 13 electrons, so if you go backwards to the first noble gas, then what you would find is neon 10 electrons. So that would be its shorthand notation. And then for gallium, 31 electrons. If you went backwards to the first noble gas, it would be 18 electrons. So that would be argon. So that would be gallium's shorthand notation. Okay, I think we're almost done here. So now let's tie some concepts together from chapter 7 and this chapter 8. So quantum numbers, electron configurations, and the periodic table. So if n is 1, L can only be 0, right? M sub L can only be 0. That's the 1s orbital. So one of those, which can have 2 electrons total. So you could have 1s1 or 1s2. If you're at the second shell, L can be 0 or 1. So M sub L can be, if L is 0, M sub L is 0. So that's the 2s orbital. So you could have 2s1 or 2s2 if you filled it up, right? Or if L is 1, you can have M sub L be negative 1, 0, or 1. That would be the p orbitals, 2px, 2py, 2pz. So you could have anywhere from 2p1 to 2p6, right? And then the same thing here, you could have 3s1, 3s2, or you could have 3p1 to 3p6 at the third shell, or you have d orbitals at the third shell, and you could have 3d1 all the way to 3d10, right? So same with the fourth shell, 4s1 or 4s2, 4p1 to 4p6. On the 4Ds, you could put 1, or you could put up to 10 electrons there. Or in the F orbitals, you could put 1 all the way up to 14 electrons there, because there's 7 F orbitals that hold 14 electrons, right? Well, the periodic table is kind of laid out like this. So this is, hydrogen would be 1s1, and then helium would be 1s2. And then if you go over here, so if you notice, so this would be the S1s and S2s. So 2 blocks. And then the P's are here. So there's 6 elements across there, 6 blocks. So that would be 2p1 over the neon 2p6. So aluminum to helium. So now if you go down another, this would be 3p1 over to 3p6. So silicon 3p2, phosphorus 3p3, sulfur 3p4, chlorine 3p5, argon 3p6, right? So that's what's called the P block. So how about the transition metals? So if you count those blocks, there's 10 of them. Well, what can hold 10 electrons? Would be the d orbitals. Where do you run into d orbitals at? You don't run into d orbitals until you get to the third shell. So even though we're in the 1, 2, 3, 4th period here, this is actually 3d1 over to 3d10 for zinc, right? So yttrium would be the 4d, so this would be 4d1 over to 4d10. And below that would be 5d and so forth. And then at the bottom of the periodic table, if you count these blocks, there's 14 blocks. So 14 electrons. So that would be the F block. So where do you run into F orbitals at? You don't run into F orbitals until you get to the 4th shell, right? So fill in these would be fill in the 4F, and fill in these would be fill in the 5F. Okay, so you could use a periodic table to write an electron configuration. So if we wanted to do this for calcium, for example, we would fill the 1s first, and then we would fill the 2s, and then after the 2s, we would come over here and we would fill the 2p6, and then we would come here and then we would fill these. So we would fill the 3s2 and then come over to the next block, and then after that is full, we would come over to here and we would fill the 3p6, and then we would come here to the 4s and 4s2, and now we're at calcium. So you can use a periodic table to write electron configurations too. Okay, so lastly, let's identify these 2 elements. So 1s2, 2s2, 2p6, 3s2, 3p4. There's 2 ways to solve this. You could just count the electrons up. So that's 2, 4, 10, that's 16 electrons. So then you go here to the atomic number 16, and that would be sulfur, right? The other way to do that would be, this is P1, P2, P3, P4, P5, P6. So P4, and this is the 2 Ps, and this is the 3 Ps. So 3P4 would be sulfur, right? Okay, and then lastly, so what is this element? So argon, so that's 18 electrons plus 8 more. So that would be 26 electrons. So what is that going to be? 26 electrons. So I'll look for atomic number 26. So that would be iron. So that would be iron's electron configuration using shorthand notation. Okay, whew, that was long. So we will stop there.